difficult. The C sequence is the sequence again. These are supposed to increment, so these are easily guessable. If you can guess the caller ID and the C sequence, you can inject into the SIP stream. If you can inject into the SIP stream, you can manipulate the signaling, which controls the entire call. If you can control the entire call, you can redirect anything you like. So fortunately, people implement these fairly poorly, so we're lucky. We can actually take over SIP streams. And then it obviously has an SDP packet, which we're not going to look at. Next. Okay, so there are 6 core SIP methods, and then there's like another 3 or 4 extra ones that they kind of chucked in. They're not that interesting typically. The main ones that we want to care about are invite, which is used to set up a call session, register, which is used to update a registrar binding, which I really hope that I have in here what a registrar is. I don't remember. And buy, which is used to terminate a call session. There's also an options packet, which is used to query a SIP device, and it is an RFC requirement that every single device supports the options method. When someone gets an options packet, they're supposed to respond with the methods that they support, their version number, the software that they're running, the VIA tags, their froms, their tos, like everything. It's really cool. You can do like all sorts of cool stuff by just like fingerprinting with options. Okay, so this is how a SIP call session is set up. You have portions of the infrastructure, which is a soft phone at one end and a SIP phone at the other end. And then you have proxy servers. Proxy servers are used basically as a single entry and exit point into a SIP infrastructure environment. So they allow you to have a whole bunch of specific SIP devices and only one domain name. So you can have a whole bunch of devices that are basically hidden behind a NAT, which would be the proxy. Pretty straightforward stuff. So anyway, we send an invite, the proxy forwards it on and tells us that it's forwarding it on, forwards it on to the next proxy, gives it to the person who's supposed to get it, who responds back. We get the ringing response, then they actually answer the phone, we get the 200 OK, we acknowledge that we've got the 200 OK, we do our like little media thing, and then we send a buy, and then we send a 200 OK, we received your buy. That's that. Pretty straightforward stuff. The state engines to handle various timeouts and that get complicated, but essentially it's very, very straightforward. By the way, this is called the SIP trapezoid. They like to talk about it because they think that using geometrical terms makes them sound cool. So you'll hear about SIP trapezoids a lot. What it really means is 2 proxies and 2 people calling each other. Boring. Next. Okay, so SIP typically carries SDP. SDP is a very, 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 very old, ugly protocol. I don't have any examples here. That's just because they make me feel ill when I look at them. It's basically based on single characters and numbers. It's like mind-boggling how they got this stuff through an RFC. Session description protocol is used to describe how an RTP session is going to work. In theory, it's flexible enough to define any media stream or any actual session. In practice, it's only actually used for RTP because RTP is the only thing used with voice over IP. It's a plain text protocol again, just about all of these are, except for the actual codecs that get sent across via RTP. Everything else is plain text. And it's going to define a whole bunch of stuff. So it defines the port. It can do a whole bunch of stuff, and if you are going to be injecting a SIP packet into a SIP stream to redirect, for instance, the RTP traffic, you're going to have to include a new SDP session. One of the cool things you can do is if you can stand in line between a SIP packet from when it comes from the original person to the destination, you can actually modify the SDP en route and add yourself as one of the destinations for all of the RTP traffic. So you can get all of the traffic sent to you by sniffing, just by modifying this protocol. Cool stuff. The media protocols, on the other hand, that's a misnomer. There's only one. It's RTP, which is the real-time protocol. Again, another very, very old protocol. As you can see, it was originally done in RFC 1889. That's now been obsoleted. It's 3550 is the current one. It supports a whole bunch of different codecs for audio, video, streaming. Like they have a codec in there for whiteboards, so you can stream whiteboards over the internet using this protocol. I don't know why you'd want to do that, but it's possible. It's also built on top of UDP, though it has to be encapsulated inside something else. It doesn't contain the. It doesn't have the ability to do anything other than define this codec, this IP, this port, this sort of activity. And this is incremented for a packet. and you only need to get it like partially correct. Okay? There's a timestamp. The timestamp is incremented, obviously, via time. Again, you only need to get that partially correct. There's a 32-bit identifier, which you don't have to get correct. Okay? You do all of that, and you can inject into an RTP stream, which means that you can brute force the key space very, very rapidly, particularly if you can timestamp the remote box. And anyone who knows anything about how to send TCP knows about how to use IPIDs or whatever to timestamp a remote box. So fingerprinting or injecting is very, very trivial with RTP. Okay, so now we know how to send data and set up data connections over IP, but how do we actually get them into the PSTN, which is where we want to have fun? This is where the integration protocols come in. And once again, there's two types. There's signaling and media protocols. So the PSTN, as it stands right now, use SS7 for signaling, which is out-of-band traffic rather than in-band traffic, such as it used to be. There's a protocol suite called SIGTRAN, which provides SS7 over IP, and these are just plugged into signaling gateways, which are then plugged directly into the internet. So if you know SS7, you can send SS7 commands straight to boxes on the internet, which will then go into the PSTN. Unfortunately, I don't know SS7, so it's going to be another year before I can give you the how to take over the entire PSTN talk. There's another protocol coming out which is supposed to replace TCP, which is being pushed very heavily. Unfortunately, the performance kind of sucks, and it's not really out there, but it's the Stream Control Transmission Protocol. It's sort of an emerging signaling protocol. It allows for like multiplexing over a single stream and like all sorts of other super cool stuff. There's a Linux kernel version implementation that's available. It's a separate patch. I've been informed that it's available by default. I haven't checked, but I do know someone who scanned the entire internet to find listening SCTP ports, and he found one. So the entire internet has got one box listening for this protocol. On the other hand, when I was doing media protocol scanning, we scanned one country and we found 37 boxes. So I think between the two, I'd rather focus on taking over media stuff. So if we look at the next slide, we'll get some information on the media protocols. As I mentioned, there's this H323-based Megaco, which is actually H248 is its designation number. Again, it's an ASN1 protocol. It's also crap. As I said, it's ASN1. There's not much else to say about it. They're trying to push it as a replacement for MGCP because MGCP is just god-awful ugly. Unfortunately, there's a lot of legacy, or sorry, fortunately in our case, there's a lot of legacy devices out there that already support MGCP. So we're going to have a very, very easy time in terms of exploiting MGCP-based media gateways because there's a hell of a lot of them out there, and now that everyone has pushed MGCP out to such a legacy level, it has to be supported by all the new software that comes out because they have to integrate with all the legacy software, which means MGCP is basically getting perpetuated. This is nice. They updated the RFC, but they didn't really update the protocol very much. There's 3435. It's a very easy to remember protocol number, RFC number. It's a very, very difficult to remember protocol. When we look at some of the live demo stuff I've got, I probably won't be able to remember what it is that we're looking at. They use things like capital Z versus lowercase z as different designators for something. I think it's the name of the host. It's absolutely horrible. A lot of the commercial stuff coming out now supports both protocols, both Megaco and MGCP. However, a lot of the engineers out there don't know how to use Megaco, and so they just go with what they're comfortable with, which means that, once again, MGCP gets perpetuated. And as I mentioned before, there's only one way of actually sending data over the internet that encodes audio, and that's RTP. So RTP and SDP actually get used along with MGCP to set up a media session between the PSTN and the internet. Okay, VoIP infrastructure. What are the actual bits that we need to worry about when we look at a SIP environment? Well, there are the SIP entities. There's a user agent, or UA, as they typically say. The user agent is anything that's at one end of the SIP stream, or one end of the SIP session. So it's a soft phone or a hardware phone, or in our case, a program which can generate SIP messages and inject them into a stream, or send them out over the internet and do something with them. You then have a proxy, which, as I said, provides a single entry and exit point for a voice over IP environment. The idea is that you only need to know the address of the proxy, and then the proxy can talk to everything else and figure out which user agent you're trying to access. For some reason, these proxies get treated as firewalls quite a lot, even though they're not. So a lot of proxies are now being marketed under the term Session Border Controller, or an SBC. An SBC is basically a proxy by any other name. It's a NAT device that supports SIP. We had an in-depth look at one of the leading ones that got purchased very, very recently, and it was horrible. It was based on Red Hat 6.2 Zoot, and it was running kernel 2.2.13, I believe. So we were able to use ICMP to overwrite portions of the kernel stack and DOS the box. That's bad. Particularly if it's your firewall. So the way that people can find particular user agents is based on registrars. Registrars and proxies are basically work together. There's also redirect servers, which get used in very, very high use environments by telcos. They do nothing but redirect from one proxy to another. They're dull. Registrars are interesting. Registrars are basically the DNS service, right? They store a mapping between an IP address for a user agent and the SIP URI. So when we saw earlier Bob at Biloxi, what happens is the proxy will get a hold of this, will forward this to the registrar and say, where the hell is Bob at Biloxi? And the registrar will go, Bob at Biloxi is 192.168. blah, blah, blah. And then the proxy will be able to forward it on. So the idea is that the registrars are dumb. They don't actually know where anything is, they get told, which means that the responsibility is on the user agent for informing the registrar of their location at any point in time. The way that this happens is the user agent will have a timeout that they will send to the registrar saying, when we get to 90 seconds from now, drop this binding and I will send you a new one. There's tricks that you can play if you can access registrars to force them to drop all of the previous bindings and update with new bindings. Just by sending contact information that says all of the other bindings that you have right now, set them to a timeout of 0, and then set this to a timeout of 3 years, and it will do it for you. Typically, these are very, very sensitive devices, and as such, there should be authentication. So there's the capability for authentication built in within SIP. However, most phones don't have that capability built in. So while the registrars will support authentication, the user agents typically don't, because no one knows how to put a username and password into like one of these things, particularly if it's a phone on a desk. I mean, like, what's your username? 1234? Doesn't make any sense. All right, so we've got like the core SIP entities, which are the user agent, the proxy, and the registrar. We then have the gateways. I've mentioned the gateway several times. This is because the gateways are the fun bits. Like, breaking all that other stuff is cool, but you only get to muck about with internet stuff. Breaking this stuff is super cool because you get to muck around with the telephone network without any security, and as a result, they're wide open to attack. Let's see. So yeah, the media gateway, RTP to PSTN analog voice traffic, and signaling is SIGTRAN to SS7. Moving swiftly onwards, the fun stuff. All right. I don't have an agenda, and I don't know what order these slides go in, so I'll just kind of talk and we'll see if it matches up. There's basically two things I want to talk about before we get into voice over IP security. And the first thing I want to talk about is the nature of vulnerabilities. Okay, there's basically two types of problem out there as far as I'm concerned. There's a generic software problem that you're going to find, and this will be in any sort of software. It could be buffer overflows, format strings, integer overflows, race conditions, all the other stuff that frequently gets so much bill and play during a security conference. These are great bugs. You can take over a piece of software. You can run your own software instead. You can take over the operating system or the host, and you could do what you like. That's all well and good. But what's typically more interesting in terms of making a lot of money is application-specific attacks. So application-specific attacks, for instance, in the web world would be SQL injection or LDAP injection, where you can take over the actual application and make it do what you want it to do. This means that you don't need to worry about writing your own version of the software. So for instance, if I want to steal someone's database, I could break into their web server, get through their DMZ environment, get into their backend, hack their Oracle box, and then try and pull all the data back. Or I could just do an SQL injection through their web app front end and pull all the data down using my web browser. Right? It's similar with voice over IP. We can find bugs